So I'd like to discuss the subject of curved coordinate systems by taking into account the simplest possible example of such a system, which is the ordinary polar coordinate systems in 2 dimensions. So the basic equations that govern the coordinate system is that the radius vector r would be given by xi hat plus yj hat in the Cartesian coordinate system. And in the polar coordinate system that we're considering, the corresponding equations would be x equals the magnitude of r cosine theta, y equals r sine theta. So you would write the vector as that, but that's still not truly a description of this coordinate system and vectors in this coordinate system unless we are able to express everything in terms of the unit vectors e sub r and e sub theta. Observe that e sub r is just a continuation of the position vector r hat, while e sub theta is perpendicular to that in the tangential direction. So as r rotates, you can think of this as describing the tangential direction to the circle that r makes when it rotates. So that's the coordinate system we want to express everything in. But right now, let's try to write some things that we can say with this particular transformation. For example, what is dx? A small change in x in terms of r and theta would be written like this: the partial derivative of x with respect to r dr plus del x by del theta d theta. So as you can see, a little change in x, which would be dx, has got in it elements of both a little change in r and a little change in theta, as you might expect. So del x by del r from this transformation I wrote above is just cosine theta, and del x by del theta from the same transformation is negative sine theta, with the r taken in. So that's going to be your transformation dx. dy similarly is del y by del r dr plus del y by del theta d theta. And if you look at the y coordinate, then that gives me sine theta dr plus r cosine theta d theta. So that gives me dx and dy. And at this point, I can do a number of things. For example, I can find the metric. The metric is defined as ds squared plus, so if I have ds squared, by the Pythagorean theorem, if that's dx and that's dy, then ds squared is basically that. So ds squared is going to be dx plus dy squared. It's a Pythagorean theorem applied to that little triangle. So what I can do is I can square that and I can square that. Let's see what I get. I'm going to get cosine squared theta dr squared minus 2 times r cosine theta sine theta dr d theta, and then plus r squared sine squared theta d theta squared. And now I'm going to square dy squared. That's all just dx squared. Now I'll be squaring dy squared. So that gives me sine squared theta dr squared plus 2r sine theta cosine theta dr d theta plus the last term is the square of that, r squared cosine squared theta d theta. Now you observe that sine squared plus cosine squared is 1. Now this and that will again be 1, and these two terms simply cancel out. So that's always a feature of systems called orthogonal systems, systems which have this orthogonality property. and that's a early signature that you have an orthogonal system in here. It's obvious from just looking at it that it's orthogonal, but that's a secondary characteristic of orthogonal systems. So putting together sine squared plus cosine squared, I'm going to get dr squared plus r squared d theta squared, and that is the metric. Now, by the way, the arc length vector ds, as written as a vector, is just dx I hat plus dy j hat. Because as you can see, if that's written as a vector, it's going to be dx I hat plus dy j hat. Well, let's figure out what that is. I'll just put that here. That's going to give me cosine theta I hat plus sine theta j hat times dr. So I'm writing all the dr terms together plus all the d theta terms together. So I'm going to get negative sine theta I hat from that and cosine theta j hat from here. And then I have the r outside d theta. This bears some thought, because what I've essentially written here is the vector e sub I, e sub r. Look at that vector e sub r. Its x component is cosine theta, its y component is sine theta. Now this essentially is the vector e sub theta, because look at that vector. The x component is negative cosine 90 minus theta, because of that angle being 90 minus theta. Well, negative cosine 90 minus theta is negative sine theta, and the y component is positive sine 90 minus theta. Well, sine 90 minus theta is cosine theta, so that's positive cosine theta. Sure enough, it's e theta. So we have written the vector form of the arc length element in terms entirely of the coordinate system known as the polar coordinate system, and its two unit vectors, which are the radial unit vector and the tangential unit vector, e sub r and e sub theta, respectively. Now, what else can we do when we have a coordinate system like this? What other thing that can we do? Well, one thing we can do is we can write the area element. The area element is not as simple as that. So for the area element, you have to consider what's called the wedge product. And sometimes you'll find it described as the oriented Jacobian transformation. They're both related to each other. So what happens is when you go from one coordinate system to another coordinate system, and you try to find the volume element from one coordinate system to another coordinate system, they're related by this Jacobian of coordinate transformations. Well, those are all big words, but basically it amounts to just calculating the wedge product. Now the wedge product has got some very simple characteristics, so if we take this wedge product approach, we can avoid this whole Jacobian talk. Dr wedge dr and d theta wedge d theta are 0, and then the only non-zero terms are dr wedge d theta, and that must be equal to negative d theta wedge dr. What this basically tells us is that dr and d theta are some sort of an area, and so when you try to make an area of r with itself, you get 0. When you try to make an area of theta with itself, you get 0. But when you make an area of r with theta, you get something meaningful. So if I have a dr here and a d theta here, you can clearly see that the area it makes is some sort of a parallelogram, and dr wedge d theta gives us a cross product type orientation, which I'll put in this direction, n hat. And if I do d theta wedge dr, it'll go in the opposite direction as n hat, so that is essentially telling us the outward normal convention there. So if we accept this this wedge product setup, you can actually find the area element dA, which in the Cartesian coordinate system is dx wedge dy. You can find it immediately in the polar coordinate system. So for dx, I'm going to write that, and for dy, I'm going to write that. Okay, so let me do that. Cosine theta dr minus r sine theta d theta I'm copying what I have above there. And then the next equation would be wedge sine theta dr plus r cosine theta d theta. Now I apply the rules of the wedge product. That's like saying dx cross dx or dy cross dy. They're both 0 because the angle between r and r is 0. So think of this as a cross product. If you don't like the wedge product, think of it as a cross product. The only thing is, in higher dimensions, you don't have the analog of a cross product, but in 2 and 3 you do. So this is going to be cosine theta sine theta. Let me write everything out. Dr wedge dr, and then negative r sine theta, which is sine squared theta, d theta wedge dr, and then I'll have these terms. So I get plus r cosine squared theta dr wedge d theta, and then negative and negative is negative and positive is negative. Negative r squared sine theta cosine theta d theta wedge d theta. Well, as I remarked before, the dr wedge dr is 0, d theta wedge d theta is 0, and then these two terms will just arrange themselves to give opposite of each other. So that's going to be dr wedge d theta. Let's agree to put r before theta. So that's going to bring a negative sign here, and that negative sign is going to disappear. So I'm going to get r sine squared theta dr wedge d theta plus r cosine squared theta dr wedge d theta, and then cosine squared plus sine squared is equal to 1, and we end up with r dr d theta. If you can write this as follows, you can write this as dr wedge r d theta. Well, isn't that very natural? Because when you have a little dr, the quantity that you want to multiply it by to get area is r times d theta. This r vector is out here somewhere. It's a big vector r, and then you extend that by a little amount dr, and then you swing it around a little bit by this amount d theta, and the excess area you have is precisely given by that. That's your dA. So it satisfies the intuition that you have about how area is swept. You extend the r vector a little bit and then sweep it out, and that sweeping arc that you get, the extra arc you get is, well, it's technically it's r plus dr times d theta on this side, and on this side it's just r times d theta, but the second order infinitesimals disappear, and you end up getting just this. So for those who are curious, this is actually related to the Jacobian of the transformation. What I can do there is I can write this as a matrix J, or sometimes called Jac, the Jacobian matrix, which is cosine theta, negative r sine theta, and r cosine theta. And the determinant of the Jac is going to be, well, let's see what it is. It's r cosine squared theta plus r sine squared theta, so it's just going to be r. So one way of remembering a transformation like this is when you have coordinates and you want to find areas or volumes or something like that, in one coordinate if you have dx wedge dy, in the other coordinate system it's going to be Jac, determinant of the Jac, times dr d theta. And here, of course, it's r dr d theta, because the determinant of the Jacobian is just r in this particular instance.